So next up on our list of reactions to talk about is the dihalogenation, usually dibromination most commonly, where we're reacting the alkene with Br2, and what we're getting is actually a stereoselective addition. So we're getting an anti-addition. Now, if we're adding two of the same thing, of course we don't have to deal with regiochemistry at all, although we will when we talk about variations of this reaction using something else. We'll get to that later in this video. But first, this is a case of we have things coming in on opposite sides specifically. So how does that happen? And you already know the answer. Things coming in opposite to each other, that's typically an SN2 type process. So we're probably going to end up bouncing up against an SN2 type mechanism later on here somewhere. But let's start off with how the first one gets in place, because that's the one that's a little strange and still many years after I saw it for the first time, still a little weird looking to me. So first, we have a symmetrical dihalogen molecule. Again, we're using bromine for this, but we could use chlorine. Less so iodine, and fluorine has big problems, so we're not going to worry about that one. What we have happening here is a simultaneous nucleophilic attack by the alkene on the bromine, and a attack by the bromine onto the other carbon of the alkene. And along the way, we're losing the other bromine. So we've got a lot going on here at once. It's kind of messy looking, and one of the reasons I've never been particularly fond of this mechanism. So we end up with this, which I hinted at in the previous videos, a cyclic bromonium intermediate. It's a cation with a bromine that has a positive charge. It still has two lone pairs on it, but it has a formal positive charge. And then in the more direct version of this, we see the second bromine coming in as a nucleophile opposite the first one. And, well, there's the SN2-like approach coming in opposite a leaving group, which the three-membered ring creates a leaving group, whether we had a good one or not. And here we are. Now, this is a case where we have selectivity that's anti, and the only way we ever get that is by blocking off the face that we started with. It only happens when there's a stepwise reaction, and it only happens when that first step allows me to block the face that my first group came in on. So in this case, that would be the first bromine is, by virtue of this three-membered ring, blocking approach to what I've drawn as the top face, or the sticking out of the page here, so that the other bromine can only come in opposite that in an SN2-like fashion to open that ring, and therefore we end up with the two groups anti to each other. That has some problems. Beginning with what happens if I have an unsymmetrical alkene to begin with. We've kind of hinted at this before, but here's where we start to see a problem, in that if I have something like this, where I have an unsymmetrical alkene, well, when I'm done, I'm not going to be able to tell, sort of. But if I go through that first step, I'm here with that, again, three-membered ring intermediate. Only now, it's not unsubstituted. Now one of the carbons actually has something else on it. There is a way of looking at this, and a problematic one, which is to say that, well, what if it's not entirely closed down? What if it is actually kind of like this, where we're now looking at something here? Now that would not give us perfect stereoselectivity, because theoretically some of the other bromine could come in from the top face here and give us the syn addition, two bromines on the same side. But it might explain something else we see. When we react with another bromine, primarily we end up with the trans addition. We end up with an anti-addition where the two bromines have ended up anti to each other. The problem happens when we trap this with something else. And there are a couple of ways to do this. You can use another halogen. You can use a nitro group. You can use the one that we're going to deal with here is water, but it's called the Halohydrin reaction, where we're actually putting halogen in place, the halo, and the hydrogen part coming from water. Well, if this were SN2-like, which is what I said in the previous case, we would expect to see this. Expect the alcohol eventually, after neutralization, to be opposite the bromine and on the opposite, less substituted carbon, because that's the more accessible one. But that's not really what happens. We don't really see that. What we see instead is this. So it's going to lead us to some questions, and that is we see our incoming nucleophile ends up on the more substituted carbon. And we've seen that before because that's what you'd be looking at if this were the active electrophile. The cation obviously would be more stable on a more substituted carbon. So that would make perfect sense if the nucleophile ended up there. But we're seeing too much in the way of stereoselectivity. So our problem with this reaction is that we're really looking at something probably more like this, where we've got one bond, which is the one that remains, which is pretty solid, and then we have something in between. So again, like I said with the mercury case, this is not a cut and dry example. We've got a case here where it seems like we have SN1-like regiochemistry if we're using something other than the bromine as our nucleophile, but we're seeing SN2-like stereochemistry. So we probably have some coordination, some equilibration between the two cationic forms, the bromonium ion and the straight cation, which would help us to explain how we get that. Now, a few things that we can actually use as evidence here. One, if I looked at this alkene, where I have an aromatic ring here, and did this bromine addition. The syn and the anti here are going to give me two diastereomers, which I can then separate. I can measure the ratio between them. I still get pairs of enantiomers, but I will get two diastereomers from how this added. And what I actually see is not a lot, not complete anti. I see about 30%. So if I draw this with those in the plane, just for simplicity here, so like this with my aromatic ring, and this for the methyl group. Well, that would be the trans addition. But what I actually see is about 30% of what would appear to be the syn addition, which is suggesting that they both came from the same side of the alkene, like so. So how did I get there? Well, the only way I can explain that is if I do have a real cation. That's the only way I'm getting approach that's not anti, is if I have a cation on the carbon. Well, why? Why would I say that that's possibly going to be the case here? Well, let's have a look. If I had the original bromonium ion from that particular example, I would have something like this, and I would have this. My aromatic ring off to the right here. Off to the left, sorry. Well, that's fine. That's the bromonium ion. That would explain the trans relatively easily, but it doesn't explain how I got syn addition or the cis product out of it. So how am I going to get that? Well, I'm only getting that if I have this, which is the actual cation on the carbon. Now, let's see how well we paid attention before. You know the answer to this. Why would I get that? Why would I be seeing that cation happen specifically? Why would that be suddenly more likely than it has a right to be? And the answer, of course, is this is resonance stabilized. Cations adjacent to aromatic rings, cations adjacent to other pi bonds, can undergo resonance. In this case, we can't do another reaction with the aromatic ring, but the resonance still helps to stabilize that cation on the carbon. It does nothing for the cation on the bromine. So we're going to see more of the product deriving from this, depending on conditions, about 30% of it ending up as the syn addition, which means more than that was actually in this cationic form, because ideally this cation would have a half and half approach. So if I'm seeing 30% of the product deriving from the syn addition, that means also 30% of the anti-addition came from the cation on the right, which means this is now 60% carbon cation versus approximately 40% cation on the bromine. There's a lot of other pieces of this mechanism, but this is one case where we can actually narrow down that yes, that carbon cation is very reasonable, even though the bromine does tend to suggest stereochemistry. In simpler examples, non-resonance stabilized examples, we can push it in the other direction when we introduce resonance to the problem. So the two things that we get out of this, one is that our halogenation, we have stereochemistry. So we have this, regardless of what's in the alkene. If we have a lockdown alkene, I'm going to see primarily stereochemistry, anti-stereochemistry from an anti-addition. But we can get regiochemistry if we have something else as a nucleophile. So if I have something like this, and I have Br2 and I have water, or I have BrCl, something where I'm going to have non-bromine as a nucleophile, what I'm going to end up seeing primarily is still the stereochemistry of an anti-addition, so like so, but I'm going to end up with regiochemistry that's more suggestive of a cation. So I've got, again, the SN2 like stereochemistry control and SN1 like regiochemical control because of cation behavior. So these two don't particularly play nice. The easy way to remember it is just that you probably shouldn't be drawing a second bond to the bromine all the time. Probably it's more like a half bond is a good way to think about it, where I have now partial charges on both. So I can explain some of what I've seen stereochemically by saying that, well, I have a partial charge on the bromine, and I can explain the regiochemistry by saying, well, I have partial cation on the carbon instead.